Hi, my name is Noah Gift, and today we're going to cover the second chapter of Practical MLOps and get through the foundational background for MLOps, including how to do things with Linux and Bash, what are the basic intuitions around the math of data science, what is potentially a data science workflow from ingestion to exploratory data analysis to modeling to a conclusion, and then how do you take these things and use a cloud-based development environment to come up with solutions. So let's go ahead and get started. There's a lot to cover, and we're going to be able to cover all of it in about an hour. And what I'm going to talk about today is getting into the foundations of MLOps and some of the necessary background material to get started with doing MLOps here. So in this book, let's just scroll up to the top of this. So in the book, and let's just start at the beginning here. So in this Practical MLOps book, the first chapter, what we covered was some of the foundational components of what is MLOps. But in this chapter, we're going to get into some of the next steps. So, what are the background skills now that we know that there's a need for MLOps? What are the kind of foundational skills that are necessary to piece by piece build on what we covered? And in particular, I think this is one of the areas that I see a lot of students struggling with is this concept of Bash and the Linux command line. And it really is actually very helpful to have experience with knowing about Bash and Linux, because most machine learning, most data science is going to involve a Linux terminal. And it is worth having a little bit of experience running Bash and Linux. And in particular, what that often means is that you're going to be using a cloud-based development environment. I think one of the easy places to get stuck that I've seen the last, let's say, 5 years or 6 years teaching machine learning is that students get a Windows machine or maybe an OS 10 machine, and it doesn't exactly do what they need it to do because it's running a different version of an operating system, and then they struggle and they can't get things working. But it has nothing to do with their ability to do machine learning. They're just in the wrong environment. And my experience has been that the cloud-based environments, whether it's AWS, whether it is Azure, or whether it's Google Cloud or some other cloud, these really are, in my opinion, these web-based cloud environments are the way to go. And I think if you start off there, it's a great place to really get a lot of expertise quickly, because you're working on the right environment. And one of the analogies that I use in the book is that imagine if you're a surfer, right? I grew up in Southern California, and a lot of people I knew were into surfing, and you want to surf every day at the beach, and you live 15 miles away. That's very inconvenient, right? If you want to be a professional surfer, that would be difficult because most of your time is driving back and forth to the beach and parking. So if you want to be a surfer, you most likely should be able to walk to the beach. Likewise, if you want to be a machine learning expert, you need to be in the same location where all of the action is happening. And so that really is the cloud. And let's just walk through really quickly. You see this example, this Cloud Shell. I'm going to go to AWS Management Console here and just talk about a couple things that you can do. So to start with, one of the really great features of AWS is they have this Cloud Shell icon right here that you can click. And what it'll do is it'll prepare a terminal for you. And all of a sudden now you can start trying out commands, testing things out. And you don't have to worry about, for example, is Python installed, or do I have the right version of this? Or it's all encapsulated in this right environment. So again, just like the surfer analogy, you're at the beach. You're not 50 miles away inland trying to figure out how to get to the beach so you can surf. The waves are right here. This is actually where you're going to start. So let's take a look at Python, for example. If I type in which Python, we can see that they've already installed Python. You can see this is 2.7. We also have Python 3. Python 3 is installed. They have Python 3.7. And what I would recommend is I like to create a virtual environment first to protect my code. You know, if we go here, we type in virtual env, and I say tilde/dot, we'll just call this cloud. You can see that the virtual environment package is not installed. So what we could do is we could try the Python 3 version. Let's see if that works. And what this will do is it'll show us that the version of Python 3 that we have here does include a virtual environment manager, and I created it in this hidden directory. I personally like to, when I create virtual environments, I like to put them inside of my home directory as a dot file so that I don't have a bunch of mess all over the place and I accidentally check it into source control. And then I want to activate it, so I type in source and .cloud bin activate, just like that. Once I activate it, you can see now that it adds this to my terminal prompt. And then if I type in which Python, you should see now that it's this Python. And then from here, you can just start going and start playing around with stuff, installing scikit-learn, installing maybe Boto 3 to play around with the SDK. So for example, if I go here and I say pip install Boto 3, this is the SDK for using all of the different parts of the AWS cloud. I can talk to every single part of the AWS cloud by installing Boto 3, and it's a great way to really experiment with what's happening in the AWS platform. I also like to do this. I'll do pip install IPython, and IPython is the shell-based version of Jupyter. And then from here, just with IPython and Boto 3 in this Cloud Shell, I've eliminated probably 80% of the problems that you'll normally have on let's say a Windows laptop or even an OS X laptop. Things are subtly different, but this is the deployment target, which is the Cloud Shell. And so now I can just go in here, I can say IPython, I can say import Boto 3, right? And I could just start experimenting and typing commands out. And in general, what you do is you make a client of some kind. You say Boto 3 .client, and then you put in the name of the service, whatever it is, S3, and then it'll go through and allow you to then make calls to it, like list the buckets or copy data. If I want to call an API, I can do the same thing. So in a nutshell, this is, I think, one of the best pieces of advice I can say is whatever environment you're using in production, whatever your company is using, use their cloud-based development environment because it enhances your productivity instantaneously. So this is a great resource for using immediately getting started with AWS. There's a couple things that are limited though in these Cloud Shell environments, and in particular, one of the things that's limiting is that it doesn't have a full-fledged IDE. And if you're not extremely familiar with, let's say, a text-based editor. So for example, if I just do this, I say echo foo, and then I put this into a file like file.txt, right? So I just copy some data and put it into a file. How do I edit it, right? I have to use a text-based editor. And so in this case, I know the VI editor, so I'm fine with this. But if you're not familiar with it, right, you can see, how do I edit things? How do I change things? And so there's a little bit of confusion here. And so what you can do instead is that you also can use the more featureful cloud-based environments, which include something called Cloud9. And so I'm going to go to that service real quick and type in Cloud9. And notice with AWS that a good way to, in my opinion, to search everything is just to go up to the search bar, and you can find pretty much every service that they have available. So here we see it's a cloud-based interactive development environment for writing, running, and debugging code. We click on this, and it gives me the ability to create a new environment. And so I think this is a very good place for doing MLOps. In particular, building computer vision APIs is build an environment around a richer set of tools. And so let's go through here. then we'll say practical MLOps, like this, and say this is a development environment for AWS. And then a few things to point out here. The first thing is that when you first create a environment, that the defaults are usually good enough for students. And notice that if you're a student, you can actually use the free tier, and maybe for a whole semester, you can just work in here and you'll be totally fine. You don't have to worry about getting charged because it's part of your free account. If you are doing something for a corporation, you may want some more RAM, for example, if you're dealing with slightly bigger data sets, and you may want to go up to a larger instance. There are actually extremely large instances as well. For example, if you go down to there at the bottom here, there's even metal instances that you can provision. So there's instances that have a lot of capability in terms of RAM, CPU. And so again, depending on what problem you're solving, you may want to build a very big instance. And one other thing to point out is that with Amazon Linux here as the default, that you can, I think this is probably the best choice because it's the latest version of Amazon Linux. And what also is great about this is, unlike your laptop, which is Windows or OS 10, you can't 100% really be sure that what you're building will work in a production environment. But if you use Amazon Linux in the cloud environment, you can rest assured that you're going to have the highest degree of compatibility because it's the same environment that you're working on. And another thing to point out is that this will time out after 30 minutes and it'll save you money as well. So again, I would recommend using the defaults here. Go through here, next steps, create an environment. And it usually takes maybe 20 or 30 seconds to set this up. And a few of the other things that are really powerful about the Cloud9 environment is that if you're building microservices in particular, the microservices have a whole ecosystem that you can test the code out, deploy the code out. All these different features are part of the experience with this Cloud9 environment. So let's give this a second here. Yeah, and usually it's pretty quick. Okay, there we go. So we've got this thing connected, and just a couple things I'll point out about this environment. Very similar to the raw Cloud Shell environment, except for it also has a navigation window here, so a GUI editor. And so in particular, let's just kind of set things up here real quick. So if I go through here and do the same thing, and I say Python 3-m venv, and I say cloud, I can also create a virtual environment. I can source it and then use it to actually test out my code. So cloud bin activate, and then notice that there's this environment directory here, and you can see that's where this README file is. So if I said, for example, touch hello.py, notice now it shows up here. And then if I double click on it, I can actually start using a real editor with syntax highlighting. And so again, if you're building AI applications, machine learning applications, this is a great environment to work with. So if we say hello, hello2, or hello say, or something like this, prints, and we say hi, and then I can just say hello say, and it does auto completion for me, and I can also just test it out. So I can either run it up here and there we go. We can see that this worked, which is pretty nice. Or I also can just go through here and just say Python hello, and it does the same thing. So my experience has been very positive with this environment, and as I mentioned, there's some deep integration here. And notice that with AWS, you can do everything from interact with your storage, so all of the cloud storage that you have. You can also go through and communicate with microservices, and these microservices, you could use them to deploy applications. And then you also have all these other integrations like your API gateway, which is the API endpoint, logging, lots of different things. Another thing that's helpful for students is that if you click on collaborate, you can actually share this environment with another student or a coworker, for example, and you can also start pair programming and when you're building something. So we're in this world where everybody's remote. People are mostly working via Zoom or some kind of conferencing system. So this is actually very helpful. In fact, I personally think you can be much more productive working remote than you can in person. And I think that this kind of environment where you collaborate is very, very helpful. And again, you can just go up here and share it with someone else. So that's just the basics of what I typically use when I build things in the cloud. Now, I'm going to go back here to this this chapter and talk about a couple other things. So one of the things here, maybe make this a little bit bigger. One of the things to talk about is that the AWS Cloud Shell is a bash shell. And in particular, it has the AWS commands built into it as well. And so if we go back here, one of the things that's interesting about it is that if I just type in which AWS like that shows me that they already pre-installed AWS for me. And so if I type in AWS help, that it will show me all the different things that I can do. So it says, this is the AWS command line interface. It's a unified tool to manage your services. And then if you just click the return key here, it goes through and it gives you all this documentation about all the different things that you can do, the different kind of output. You can have JSON output, you can have text output. And if we scroll down here, they'll even tell you all the different services. You can see that you can now, because they pre-installed all these tools for you, you can access literally every single thing inside of the AWS platform without having to install things. So again, if you're working on your desktop and let's say you're a student and you're assigned a project, you could take the whole semester and try to get all this configured and then you're never getting anywhere. Or you just go right to the cloud environment, get access to all these services. And let me show you an example of this. So if we type in AWS S3 LS, what I'm doing is I'm telling AWS I want to investigate the S3 object storage and I want to list everything that's in my storage. If I run this, there we go. We can see that this is all of my storage, and I could even pipe this out to some other command. So in Bash, you can take output, pipe it to another utility, and I could pipe it to less, for example. And then all it does is it lets me kind of scroll through, but that's what the less command does. Or I could even pipe it out to a file, right? So I could go through here and I could say, buckets.txt, just like that. There we go. And then if I look at it, if I say cat buckets, you can see that I printed out all these buckets. So really helpful integration. That's deep integration. And that's just one service. I can talk to microservices. I can talk to AI APIs. I can talk to machine learning systems like SageMaker. And this is really the advantage of using the right tool for the job. Again, using the beach analogy, I'm at the beach. I'm surfing the waves right here. I'm not driving to the beach to get to the place where I can park, get my surfboard out, right? This is the environment that I'm using to build the services. So just important to point that out. Now, as I mentioned, the more richer editor here for cloud-based development is the Cloud9 environment. And And what I like about the Cloud9 environment is that if you are building production services, it's probably the right tool for AWS because of the fact that it has the deep integration and lets you test out the microservices. I think the Cloud Shell is better for like very quick experiments, or if you have extremely strong Linux skills, then it could be a great environment to just be very, very productive in. But I think for most people, the cloud-based environment for building machine learning applications is good because they have things like completion, syntax highlighting for multiple languages. And in particular, the cloud-based environment has a lot of support, or there's a lot of action, I guess, in the top 3 languages. Like I would say Python, Go, and Node seem to be, for data engineering, machine learning, seem to be some of the strongest languages with the most developer support. I think the most popular is Python. For people that are doing more data engineering, there are some reasons maybe to use Go because it has a higher performance. And a couple things I'll point out about the Bash shell in particular is that you actually can configure a lot of the Bash shell, and that can be helpful for a project. And that's done with your bash RC file. So if we go back here for a second and we just do ls-l and we do this bash RC, notice that this bash RC is where this environment is configured. And what we can do is actually look inside of it and even edit it if we want to. And notice that inside of here it says that it's sourcing these global definitions right here. So this is actually something created by the Amazon Web Services team. They give you a bunch of commands automatically and change your path so that you have access to all these AWS utilities. But you could actually edit this yourself a little bit and change it. And a good example of this would be that if we go here and I type in, let's say make a change to this, we can type in echo, I loaded the bash RC, and then what'll happen is that if I source this file, that it shows me that actually I'm executing those commands. So what this means is that every time you open up the editor or your environment, you should be able to source this over and over again. So let's go ahead and try it. And let's see if this works. There we go. I loaded the bash RC, right? So if you're working on a Python virtual environment, for example, remember we had a Python virtual environment. So let's go ahead and source that. So if I go back to this file here, bash RC, we can actually add that command, and I can say here, we can say source tilde slash dot cloud bin activate. And what's nice about this is now I can start to customize this environment because I have Linux capabilities, and maybe even add a note here that says sourcing virtual environments next, like that. And then if I save this, I can again just maybe close this Cloud Shell, and go back here, open up a brand new one, and it should, there we go, we've sourced it automatically. So really having just a little bit of experience with knowing how to use the bash configuration is really helpful because you're able to save time. And that's really why configuring bash and using it is really a helpful thing to do. I think we covered this a little bit, but in bash as well, you can list files by using the ls-l command. If you want to run commands, a really good place to figure out what's happening, and I think I did this several times, is to use which. And what which does is it tells you where that's located on your operating system. And in particular, this is helpful for these kind of environments because you want to verify which executable you're actually using. So if I type in which Python, in this case, notice that it's using the Python that I created. But if I deactivate the virtual environment and I type in which, notice that it's using the system Python, which could be a problem for me because the system Python has libraries that are installed that may conflict with my project, or maybe they're older. And so knowing the which command in particular is very important because it allows you to specifically know what executable you're using. Likewise, you could have installed two versions of a tool, right? Let's say it's a data science tool or PyTorch or TensorFlow or some library like that, and it has got an executable with it. You may get confused because something's not working properly, but one way to debug it is to actually use the which command. And the which command, if we go which AWS, you can then say, okay, well, let's check out what this is. And then if you went through here and you can actually put the full path, I think you can say version. Does that work? Let's see here. Help, or is it dash version? Let's try that. Yeah, there we go. So I could first find the utility that's actually being called by using which, then ask it what version it is. And it's, let's say for example, this was an older version. I could go, I didn't realize I was using the older version of the utility, and so I need to install the new version, and then I need to explicitly make sure that I have the path to the new version of the tool. So this is a very, very common workflow that you can help debug by just having a little bit of understanding of the bash terminal. I think we also covered this as well, as that it's important to know that you can pipe one command into another command. And that's one of the benefits of the bash environment, is that most output is like a text-based output, and you can of commands in the bash terminal, and you can pipe that into another one. So a good example would be this command right here. So let's go ahead and run that. If I go back here and I say, for example, here I say ls-l, and I do, first let's look at it. It just shows me what's, lists the files, but I can actually pipe that to another command called word count. And what the word count does is it actually shows me how many lines of output there were, right? So in this case, this is line 1, this is line 2, this is line 3. So you're able to actually do a lot of powerful things by piping one command into another command. Likewise, I could do this. I could do echo, and let's actually add foo.txt, or let's add this, and we'll pipe it into out. And let's actually add maybe 2 words. Let's say foo bar, like that. And then if I type in word count -l out, you can see that it says there's only one line, but I could do words, and it shows me there's 2 words, right? And so each of these are totally separate commands, but you can combine them together. And this is very helpful actually for data engineering, because you oftentimes need to manipulate some data or change some data, and you could use a GUI tool, and it could be a very long process. Or if you have some Unix expertise here, bash expertise, you can very quickly solve a problem. Like a very good example would be truncating data. If you needed to make the data set smaller, that would be a good example of a data engineering task. For navigation, it's important to know, a couple things like PWD shows you where you're at, and then CD will move you into a directory. I think we just talked about this, the input and output. You can pipe things in and out. I think the 2 most common ones that you'll see would be, again, writing something out to a file would be this greater than operator, and then using another tool, piping one output to another, would be this pipe command. And this is what I was referring to earlier, that this is actually one of the most interesting examples I can say that comes up in machine learning, is that oftentimes you're working in an environment where you're working with a data set that's just too big. And you may have already encountered something like this. And now what do? Well, you could do a bunch of stuff and work for like a week on solving this problem. And it could be a lot of work to figure out how to deal with it. Or you could run one command. And in particular, notice that this command called shuffle here, what it does is it actually randomly samples the data and explicitly says, I only want the first 100,000 rows. So if this was, for example, I think in this case, it takes a 1 gig file and just grabs the first 100,000 rows out of it and then writes a new file. This could basically solve a very complex problem quickly, right? Because if you're doing something with, let's say, pandas, for example, and it has constraints with memory, you could do a bunch of stuff in pandas and really struggle with it, or before it even gets to pandas, sample the data and truncate it so that you're dealing with a smaller data set, and then you can test out your pipeline without having to deal with the data. And I think this is one of the more powerful things to be aware of, is that before you're working on something that you're struggling with big data, a lot of times you can make the data a small data problem, get your pipeline set up first, then once your pipeline is solid, then work on the big data problem. And I see this a lot in student projects. I see this a lot in real world projects when I'm doing machine learning consulting, is that a lot of times people get stuck because they're working on the big data problem, but they should be working on the small data problem. And this is a heuristic, which is, does anything work, right? I think that's one of the most important things to be aware of, is does anything work, versus let's try to get it working in the fancy environment with the big tools. First, make it smaller, get your pipeline set up. So that's why having some Unix utilities is really important. I did just talk about this a little bit, is that in the bash environment here, you can actually start to automate things a lot using these config files. And in particular, there's Z shell and bash are probably the two most common shells here. And I actually use Z shell for OS X, but when I'm in a Linux environment like the AWS environment, I'll use bash. And again, it's just that bash RC, and you can see there's a whole bunch of things you can do. You can maybe use API keys inside of there, which is really helpful for development. You could go through, add the path to something, source code, lots of different customizations. And as you get more and more familiar with the Linux environment, it really is helpful in building things. Another thing that's important to be aware of as well is this concept of the shebang line. And you'll see this a lot, is that as you get more and more familiar with, let's say you're truncating the data before you pull into a machine learning pipeline, is that instead of just typing the commands over and over and over again, eventually it's helpful to actually go through and make a script. And with bash in particular, you can build a script quite easily. And really the process is only a few steps. The first step is you need to put a file together. In this case, you need to add the shebang line. In this case, it would be telling the script that we want to use bash to execute this script. And then you need to make it executable by doing chmod plus x. This just tells the operating system that this file can be run as a script. And then you go through and you do / and run it. So let's go ahead and do that real quick. So if I want to make a new script here, and we'll call this hello.sh, like that, just you can say touch, and that actually will create an empty file. And then if I double click on it, I can just do the same thing. I can say user bin env bash, and that's the shebang line. And that just tells the operating system that bash is the executable that will run this code. And then we can just put in something hello from bash, like that. And now we could just do this. We could say bash hello, and that will work, right? That will work. But it's better to get in the habit of doing this, which is that you make the file executable so that way some scripts you might write in Python, some scripts you might write in Bash, some scripts maybe in some other language. And now I can just do // And when I do // it means that look inside of my file and it'll automatically figure out which executable to use. And there we go. You can see that it actually works. So for data engineering to allow you to do machine learning engineering, it is helpful to have a little bit of Bash knowledge, and you'll see that you can start to build utilities that are helpful. So as I mentioned before, kind of the surfing environment here, that it's easy to only focus on, let's say, deep learning or data science, and then not realize that you're basically still in the parking lot at the beach. You're not at the beach, right? Really, the location almost always that you're going to be using when you're doing machine learning is in an environment that has the capacity of near infinite storage and near infinite compute. And it's all got to be in one location. Now, if you're working for an extremely large corporation, I don't know, Tencent or something, or, Facebook or something like that, then they have basically the same thing. But for most people, you're going to need something like the cloud, and inside you're going to need to have the ability to do infinite compute or near infinite compute and near infinite storage. So what that means is that you're going to put it in something like Amazon S3. That storage, you don't have to move the data back and forth anymore. And then you're going to be able to do whatever it is you need to do. It could be running a MapReduce job with Spark. It could be telling a utility like SageMaker to go in and actually train a model and then put the model back into this S3 location. So this is really the beach, right? And I think this is an easy place for people to get distracted, is that they're really interested in deep learning or the algorithms or some other part of the problem. But I would call that you're at the parking lot at the beach and you haven't even gotten out of the car yet. You're talking about what you're going to do when you get to the beach. This, when you're in the cloud, is you're on the waves, you're surfing, you're doing all the different things. So I think it's very important to be aware of that differentiation. Is where are you going to deploy your machine learning model, work in that environment, and actually be in an environment where you can do things that have the ability to infinitely scale up and down. And in particular, another thing that I think is interesting with cloud computing that isn't talked about enough is this concept of the platform. And really, if you think about many things that have occurred with computer science, with engineering, is that there's an infrastructure, right? There's a platform that's available. So a good example of this would be if you look at the electrical vehicle industry in the United States, that the leader right now is Tesla. And one of the reasons that they're a leader is that they have very good battery technology. But the other thing that they've done is they have a whole infrastructure of charging facilities. So they have the platform, right? So they have the ability to distribute that charging all over the United States. And they've automated a very difficult component. Of course, you can manually charge a vehicle yourself and maybe even build your own charging stations all throughout the routes that you go, but that's a lot of work. Likewise, with cloud computing, they have the platforms that automate the different stages of the pipeline. And this is really something that's very difficult to replicate if you're a company. And I think it's the classic mistake that someone would make in general, is that they try to build something themselves versus use a technology that's already done for them. And I call this concept the automator's law, is that it's easy to get caught up in wanting to do everything yourself, build all your own technology yourself. But once people start talking about automation, whether it's self-driving cars, data centers, factories, eventually things will get automated. Likewise, a lot of the components of machine learning are getting automated. So why would you do something poorly that is already available in a more sophisticated manner? And I've seen this in lots of different industries. And a good example of some of the automation is the AutoML capabilities, right? So you could do a lot of these things yourself with machine learning, but what we're seeing from these platforms is that they're doing hyperparameter tuning, they're doing the scalability aspects of it. So again, you could do this, but why would you do this if the tool is already allowing you to automate some aspects of it? And I think a good example would be that, like, for example, if you look at Excel, Microsoft Excel, you can do linear regression, right? You can just take a column and then regress against another column, and you don't have to write any code. That's machine learning. You can do machine learning already. That's AutoML inside of a spreadsheet. How is it even possible that we're not going to have the same capabilities with other parts of machine learning? Of course, these capabilities are going to get more and more sophisticated. And so I think if you're fighting the automation, it's a very bad place to be. You should be embracing the automation and using the best tools you can use for the job at hand. And I think that's really the basis here with MLOps platforms, is you're using the best capabilities. And a good example that I brought up was that there's an economist that's a columnist for Bloomberg, and he talks about how when he grew up, he played chess, and a lot of people were angry that the chess software was beating humans, or they think it couldn't beat humans. But ultimately what they discovered was that chess software plus the very best chess players are actually better than the chess software by itself or the humans by itself. So I think that's really what we're going to see as well with machine learning and machine learning operations, is that humans plus very sophisticated software will beat the software by itself, and it will also beat the human by itself. And so that's my recommendation, is be sophisticated, but also use the most sophisticated tools at the same time. So let's talk briefly about, how would you get started with cloud computing? They actually have a very detailed breakthrough of cloud computing with Python, but just from a high level, one of the things I would recommend is what we just went through, which is whatever cloud environment you're in, that you should use a cloud-based environment, a cloud shell, because it has the built-in integration. It allows you to work in the environment that you're going to deploy to. And it's very simple to set up the foundation for MLOps, which is that you can check out your code in GitHub. You can go and set up continuous integration. You can also set up continuous delivery, which is deploying your code automatically. So in a nutshell, the cloud-based environment is really the best practice to get started with building an MLOps pipeline. So in a nutshell, as I was saying earlier, that the cloud-based environment is an ideal place to do machine learning because of the fact that that's where all of the resources live. And another thing to point out here as well is that a lot of times, I think there's some complaints about testing and linting code. I've heard many people, talk about, well, why are we doing this? And I think it's very similar to this concept of a RoboVac. So if you think about your house, or you've seen somebody that has a RoboVac in your house, imagine saying to someone, why would you want to have an automatic vacuum cleaner? I think then someone that's had one would say, because I do less work. That's the whole point of the RoboVac, is that it automatically goes through, gets the dust, cleans it up. It doesn't mean necessarily you never have to clean your floor, but it's much less work. Likewise with building projects, if you have some tests or you lint your code, this is really a cleaning process that makes it so that you have a higher quality control mechanism for your project. So that's really, I think, the best analogy for something like, continuous integration, continuous delivery pipeline, is it's a quality control check that makes it less work, even for student projects or small experiments. Now let's really briefly talk about Python here. This is really the primary language for most people that are doing cloud computing, DevOps, machine learning. And I think one of the reasons is that it's built more for a human. But I also want to say that there are some problems that I think newcomers to Python may not be aware of. And in particular, one of the problems is that it has a very poor performance. In particular, it has a lack of true threads. And so, if you use a language like C#, for example, or Java or Swift, they have the ability to send processes to a queue, and then a bunch of operating system threads will go through and do things in parallel. Python just doesn't have those capabilities. So if you are building something that's maybe like a data engineering task, there are some problems that you have to be aware of. Also, it doesn't have a just-in-time compiler like other languages, again, like C#, where the performance is very fast for single-threaded code as well. And also, it doesn't have type inference. So other languages like C#, F# can figure out what the types are. So there are some problems with Python. I think that it's good to be aware of those problems. But in particular, I think Python got lucky because of a couple of different things, and this is why so many people use it, is that it works pretty well for cloud computing, because cloud computing is really its own operating system, and a lot of the heavy lifting is done by utilities like SQS or Lambda. And I think that's one of the things to be aware of, is that because you're working in the cloud, you shouldn't be doing threads or concurrency yourself. You should use the cloud's concurrency mechanisms like SQS, for example, which is a simple queuing service. So let's go ahead and take a look at the SQS real quick. If I type here SQS, simple queue service, what's really interesting about SQS is that it has the ability to do a pattern that would be similar to the pattern that you would do if you were going to write this code in Java or C#. So you have a producer, and that producer maybe would send messages. You would have some queue in Java, and then you would have consumers that would pull things off of that queue. And again, if you're using a language that has native threads, then you can actually build very performant systems and scale things between a bunch of servers. This is not a good pattern for Python because you have to use other things like processes, which are more heavyweight. The performance of the computationally is not that good. So what do? You just not do things? Well, in Python, fortunately, if you use the cloud as an operating system, the same pattern works well. And that SQS, you can have Python producers that are single-threaded that just send network messages. So the CPU performance really doesn't matter. And so this is really one of the ways that Python has kind of accidentally got lucky, is that the performance in many cases just doesn't matter because the cloud itself is written in other languages that are high performance. And those high performance languages, they built patterns on top of them. So it's just something to be aware of, is that if you are using cloud computing, you should use the cloud native features that enable you to do things at a high level and have high throughput. A couple other things that I'll point out here about Python. So I was at a talk in the Bay Area where Dr. Patterson, who's a retired UC Berkeley computer science professor, who also created the TPU, or co-created it, the TensorFlow processing unit, he mentioned in this talk that Python is 64,000 times slower than operations in C. And so that's a pretty big number, right? That's a very, very slow. And this is actually from his talk, that he talked about how the matrix multiplication relative speed up to a Python version or an 18-core machine is that, again, you can do 62,806 times faster. So basically, the Python performance is quite bad in terms of other languages. And so really, this is a problem where you shouldn't be using Python for high performance computing. You need to use frameworks or tools to do the work for you, or else you're basically wasting your time. Simultaneously, I think one of the things that's been happening is across the world, people are more interested in energy efficiency. I know that certain countries have actually cracked down on Bitcoin mining, and Bitcoin mining is very energy intensive and potentially even a waste of energy. We don't even know yet what Bitcoin is useful for. It's actually involved in a lot of criminal operations, but we don't yet have a use case for it, and maybe we'll never have a use case for it in society. And so that's just one example of energy inefficient. Likewise, Python is 50 times more energy, uses more energy than something in C. And so if you look at potentially other languages here, C, C++, Rust, Fortran, you can see that in fact there's a real big problem with Python in terms of the amount of energy. It's one of the most energy inefficient languages that exists. And that's yet another reason to let the cloud do most of the work. And if you are using Python, have it more as an orchestration, because you're burning a lot of energy by using Python. And so I think one of the other things that I'll mention as well is that with cloud computing, that I think some of the subsets of Python are more useful, or data science, than maybe like a more computer science oriented version. And a few things I'll point out here, that in particular, the Python prompt, just the regular prompt, is a great way to play around with the language. And this is one of the advantages of Python. You want to build a function here. So if we go to this environment here and I just type in Python, right, a regular Python prompt, you can start to write functions without doing anything. You can just say hi, right, and here's a print function, or you could say even define a function even in line like this, right, a one-liner. This is a great way to play around with Python, and in particular, one of the things that you'll see here is that you can actually start to build these functions as a unit of work. And that's very different than maybe a traditional computer science view of Python, where you're building these really complex abstractions and object-oriented programming. Most of the time, when you're building something for machine learning or cloud computing, really you just want a unit of work, which is you have a function, and this function in this case is an add function, and it takes two inputs. It takes an x and a y, and then returns back an x and a y, and then you can do things with that work. So if we again go back here and we build something similar, we say add, and we say x and y, and then we just say tab this and say return x plus y, x plus y. I can actually just start to play around with this unit of work and add 1 and 2, and returns back 3. So this is really the basis of machine learning. You put something in, you do a prediction that comes out. Or you want to do distributed computing, you build a function that you take somewhere and you distribute it in the cloud, maybe SQS, or you distribute it to Lambda. And this is really the fundamental aspect of Python to be aware of, is that it can be a function that does work and returns things. Similarly, another thing to be aware of, which we got into a little bit earlier, is that you can take code and build it into a script, and this can really be helpful to automate different parts of your pipeline. And this particular script here, notice that just like with Bash, that you can actually add this shebang line that says pound exclamation point user bin environment Python, start to play around with some piece of code, and then run it as Python. So if we go back here again, and let's just maybe make another shell here. Let's just close this, and let's say file. I don't know where this run, I don't know where that shell went to, but here we go, new terminal. Let's do this. We'll say source tilde cloud bin activate, and I could do kind of a similar thing here, which is I could say, touch, or actually we can actually just use this file and just change it to using the shebang line. So if I go here and I do this user bin env Python lowercase, this just tells this executable that it's a Python executable. I can do the same thing I did before, which is I can say chmod plus x, and we say hello.py, and now I can do the same thing. I can just do hello like this, and then the interpreter knows the interpreter that's being used is the Python interpreter. So this is a great way to build utilities and play around with code, is to use that same like very simple script mechanism, which is use the shebang line. You write something in Python, do chmod plus x to make it executable, and then kind of run through and build it. Another component that's necessary to build the foundational knowledge for machine learning is to know a little bit about the concept of descriptive statistics and normal distribution. And this comes up a lot in that many things are normally distributed in the world. And a very good example of that actually is height and weight. And so, if you think about it, this is very intuitive. When was the last time you saw someone that was 7 foot tall? It doesn't happen. I've used to play basketball, so I would play with basketball players that were 7 foot tall. So even then, it was very rare to play against a 7 foot basketball player. It was like very uncommon. So likewise, it's very uncommon to find people that are extremely short, right? If they're 4 feet tall. So normally people live inside of this bell-shaped distribution, and so here's an example where you could look at the height and weight here in pandas, and you notice here that in general, if we plot things out by using Seaborn, that most people are kind of in this middle area right here. This is where the most of the distribution is, and this is something you'll see a lot in data science, and I think it's an important intuition for the world, is that whenever somebody claims something unusual, depending on what the category is, you should be cautious of extreme claims, because most things reside within a normal distribution. There are situations like events, for example, that are rare, and those are different distributions, but it's a good intuition to have. And when you're doing data science and you're building machine learning, one of the ways that you can do this in Python is to use describe. And if you do a describe, it will show you all of the descriptive statistics. So on one hand, you can plot things and you can see the normal distribution, but you also can describe things. And when you describe things numerically, you can see actually even more specific things. Like, for example, this particular data set has 25,000 observations, which is actually useful to know. Like if I go back here and we look at this, on one hand, we can tell that there's a lot of observations, but we don't know how many. But if you go back to the numbers, we can see, 25,000, all right? And we can look at the mean, which is the average, which is more prone to outliers. And we also can look at the median, which is the 50th percentile. Notice, because this is very normally distributed, that they're actually identical. And also notice that if we look at the mean here, it's 67 inches for height. It's very close, the mean and the median. The median just means it's the center, the exact center, and 50% are below and 50% are above. And that's the best way to think about a median. And then also you can look at the 25th percentile, so the first 25% or the 75th percentile, the last 25%. And you can also see the maximum observations, which can be very helpful when you're building your knowledge of the data set. So if we scroll down here, let me just get some water real quick. So if we scroll down here, another thing that's helpful is that in this case, we know that we're looking at height and we're looking at weight. And one of the things you can do is you can do a joint plot, and you can actually plot and visualize both of the distributions of the variables at the same time. And this can be very helpful if you're looking at features in a machine learning model. And we can see that they're both bell-shaped distributions, which again shows that the most of the observations are within a normal distribution. And you could even break this down further, because the median, you could actually break things out into standard deviations. So what's the average difference between observations? And once you get to around here, let's say about 3 standard deviations away, these become very rare events. And so again, if people are claiming things are happening over here or here, you can say from a statistical standpoint for a normal distribution, it's less likely or extremely unlikely that something's occurring. And this is the basis actually for quality control, where in manufacturing, a lot of times you will send an alert if something is on a rare, if it shouldn't be occurring and it is occurring. Let's say you're making bolts, and the bolts should be within a certain size, and then you're getting bolts that are multiple standard, like 4 standard deviations away from the normal observation here, the median, then you're going to maybe stop what you're doing and investigate what's occurring. So machine learning does heavily build on the idea of a normal distribution, and that's one example. There's another one though, which the author Taleb calls fat tails, and that's hard to predict and rare events that can significantly affect the world. One other one that's an interesting one that Dr. Koonin mentioned in his book Unsettled is that there things like climate change and also the environment can be very challenging to predict. And I think there's I think a lot of back and forth. People are talking about can we predict what's exactly going to happen or not? And I think the intuition, without getting into the details, is that the more variables that you add to a system and the more complexity and dynamic the system is, then the more difficult it can be to really make a prediction. So it's important to be aware of extremely dynamic and complex systems. So a good example would be self-driving cars, that it's possible that we have the technology to build a self-driving car, but one of the problems is that we have so many dynamic aspects, roads, people, other vehicles, that it could be difficult to create a complete, a complete solution. Same with the human body, counting calories. So there are some domains where you do need to be a little bit more cautious when you're making predictions. And in particular, one of the things about machine learning is one of the fundamental problems of machine learning is this concept of optimization. And at the heart of deep learning, it's the gradient descent algorithm, which is you're trying to find the global minimum. So you're trying to find the optimal solution, but not get stuck inside of the global, the local minimum. And so a good example of the intuition behind this is that imagine that you're walking down a mountain and it's dark and you don't know exactly where you're going. Well, it's possible you could get stuck on one part of the mountain that maybe has a lake or something like that, and it's not actually the bottom of the mountain. You're only halfway down the mountain. That's a local minimum, but the global minimum would be all the way down at the bottom of the mountain, is where you want to go. So one of the things that I think is an interesting heuristic to be aware of is that you can do things in multiple ways other than just machine learning. And in particular, a lot of researchers are writing things in symbolic notation. And so it can be confusing sometimes if you look at research papers or you look at mathematical notation, you're like, hey, what's happening here? But in fact, you can do the same thing in other tools. So for example, if you want to sum things in a spreadsheet, you can just say sum and it will add x1 to x6. If you want to sum things with notation, you can build the symbolic notation for it. If you want to sum things in Python, you can do it like this. So that's, I think, an important one to be aware of, is that the notation is relative and that you can do the same thing that you do in symbolic notation as you do in a spreadsheet and as you do in Python. And so it's good to be aware of that distinction. Now, one of the things that I think is a good concept to be aware of is this concept of a greedy algorithm. And because greedy algorithms are used a lot in optimization, it's important to know how they work. And so the concept is that you choose the best solution you can and worry less about the perfect solution. And we use these actually all the time in life. Like, for a good example would be, you go to the grocery store and you find some peaches at the grocery store and maybe they're on sale and they're $1.50 a pound. The greedy algorithm is, hey, I'm already here, $1.50, that's pretty good, let's buy the peaches here. Like, if you want it to be exhaustive, you could go to every single grocery store and look for each peach, and that could take you a long time. And then you could maybe ultimately figure out that that's actually the lowest price. So if you find a good thing, take the good thing. That's really the concept. And so the same thing, if you're making change, here's an example where if I wanted to make change for this, one of the algorithms intuitively is always start with the largest coin, go to the point where I can't make any more change with it, then go to the next largest coin, then go to the next largest coin. And so here's an example of a recursive algorithm here, is that basically what I do is I take the coin, take the largest one, and keep recursively giving back the function into itself so that I am able to do a greedy match on the change that I want to make. And so we can see some similar things here. Let's just scroll down here to the traveling salesman problem, which is also an optimization problem where there isn't a perfect solution. With the traveling salesman problem, the concept is I want to travel all over the world or a region, and I want to find the optimal route. Well, there isn't a perfect solution that exists, but one of the things you can do is you can use, again, a greedy algorithm to find a good enough solution. And so here's an example of some values here, different cities. And if I want to go through and I want to go from Apple to eBay or Apple to Google in the Bay Area, one of the ways I can do this is I can start with randomly picking a city. And so in this case, we say I want to randomly pick a city to start. And then all I do is I just find the shortest path. If there's two paths, let's say I can go to one city is 10 miles away, another city is 25 miles away, always pick the shortest one. And then you just run a simulation. So you go through and you go over and over again. And we can actually go down to the bottom here and see this, that basically if I run this greedy algorithm 25 times, notice that it will eventually find the best solution or that I can find within those constraints. And that's a reasonable way to solve problems that don't have a perfect solution, is that you do a greedy algorithm, pick the best choice you can at the given time, run a simulation over and over again, and then find the best possible answer for the simulation and then go with that. And again, I think you could use the same greedy algorithm for the example of the peaches, right? Let's say there's 3 grocery stores that are next to each other. What you could do is you could actually, instead of going to 10 grocery stores that are in your area, just go to the 3 that are next to each other and check the price of peaches at all 3, find the lowest one, and then buy those peaches, right? It's intuitive, and that's what's nice about a greedy algorithm. And in general, I think it's a good thing to play around with to give you some intuition about how optimization works in terms of machine learning. And as I mentioned, this is really common in life. We have optimization problems all the time. And the important thing to be aware of is that there's local minimum, which means that it's not the ultimate solution. And then there's global, which is the optimal solution. And this is, again, the intuition behind the gradient descent algorithm that people use in deep learning. So one other thing to be aware of as well with machine learning and deep learning is that in some cases a GPU-based training solution could be better, but in some other cases maybe a CPU training solution is more lower cost. So it really depends on what it is you're trying to do, and that's really a cost basis as well. So maybe in some cases the deep learning example with GPU, this would be great because you want to get to a global minimum, but maybe if it's something that's maybe a quick experiment, maybe you actually are okay with a less powerful cluster of CPUs that are cheaper, and maybe you get stuck here at a local minimum and you're okay because it's good enough, it's better than your other experiment. And so things are definitely a trade-off. Now, one thing I would also recommend, let's take a look at this playground here, is that with a neural network playground here for TensorFlow, I think is one of the best ways to get the intuition behind how deep learning works. And here's an example that epochs are basically iterations of your training. And again, you're trying to go down and you're trying to find the optimal global minimum. And if you go here and we click on this, notice that it goes through and we have our training and then we have our test. So the training is training the model, and test is basically validating that in fact we trained things and not overfitted. And so you can experiment with, if I change things around or use different data sets, what happens. Now let's use a more difficult data set. Let's pick this one. And if I wanted to predict it, notice that it doesn't converge quickly, right? It's actually a very complex problem to try to solve. And so you're going to use a lot more iterations, and it might be easy to get stuck in a local minimum. But eventually, as you start to go longer, it starts to get better and better and better. Now, one of the things to be aware of is that you can change the learning rate, and that's one of the things that you can play around with. So if we go here, does that actually fix things a little bit? Does it make it converge quicker? These are all things that you can play around with when you're learning about machine learning. Likewise, regularization is something people use to prevent overfitting. And overfitting would be if your training is much better than your test, you're doing some overfitting. So again, I think if you're playing around with deep learning and you're experimenting with it, a tool like this is a great way to just intuitively understand what's happening. And if we go back here, a good, the mathematical aspect of it is that when you're changing your learning rate here, the thing to consider is that you're going through in each iteration, each epoch, you're learning more and more. And so if you have a reasonable learning rate, then eventually you'll get to the global minimum. But if you have the learning rates too low, then it's possible that you'll just take a long time to converge to the correct solution. And this could be really expensive computationally. So you want to experiment with the right learning rate. Now, it's possible that the machine learning platform will just do this automatically for you. And I think there's definitely cases that we see where platforms are doing this. But it's also worth pointing out that if you set a learning rate too high, you'll actually oscillate back and forth, and you basically won't get anywhere. And so I think that's really one of the other intuitions about the deep learning rate is that there is a right optimal learning rate to get to the global minimum, and it really does take some experimentation. And one way to play with this is to kind of use a tool like this so you get more experience with what happens. So for example, if we go back to this data set here and notice that I want to change the learning rate super high, what's going to happen is it's going to oscillate. So basically it's not going to get anywhere. It's going to be stuck. Notice how it just does nothing, right? Because the learning rate's so high, it's just oscillating back and forth. It can't learn anything new. But if I go back here and I change the learning rate back to what it was before, notice it's quickly converging because it's a reasonable learning rate for this problem. So there's no substitute for just learning and experimenting with a data set to understand it, and also with tools like this so that you can get the intuition behind deep learning. A couple other things to point out about machine learning, key concepts, is that machine learning is the ability for a computer to learn how to do tasks by learning from the data. That's really, in a nutshell, what's happening. And so there are three different core categories for machine learning. We've got supervised, we've got unsupervised, and we've got reinforcement learning. So in general, the supervised learning here, let's go here. The supervised learning here would be that you have historical data. So in the case of the height and weight, we already have the historical data. We can predict the height from the weight. So we know that that's actually labeled data that is something we would do a prediction with. And that's a very common form of machine learning, like stock prices or anything where we've got historical data. Unsupervised is a little bit different because we don't even know what the correct labels are for the data. It could be that they're a new label that we're actually creating, and that's why people use unsupervised machine learning techniques like clustering to figure out hidden patterns in the data. And so it's essentially a kind of invention. You're basically like running through and figuring out what things fit together and finding patterns, like who are my highest paying customers or who are the best NBA players. And then reinforcement learning is a third category where it's more of like a pet or a child, and you're training them to do an action, and they learn from being reinforced, either a positive reward or maybe a negative reward. And in particular, if we look at, here's a good example of something I did a while back, where this is a clustering I did on an NBA season. And notice that I have multiple clusters here. And I discovered these labels. So I created these labels myself, which are, we just know actually, I think last night, Kevin Durant was actually one of the best players for the Olympic team for the United States. And actually, this was from several years ago. I did a cluster, and it says that he's the best player, right? So it discovered something from the data and showed that this was one of the best players. Likewise, if you look at this cluster, because these players here have a lot of assists, and so we can see the assists here are large circle, that these are people that are very good at passing the ball. And we know Steph Curry is one of the best players in the NBA, and we can find him in this cluster. Chris Paul, also, this was from several years ago. I think it was 2016. But he went to the NBA Finals again. So we were able to find these patterns, even though we didn't explicitly say what the labels are. And that's really the advantage of the unsupervised machine learning, is the discovery of these hidden labels. One thing that does come up a lot with k-means clustering is how do you actually discover the correct number of labels. And one of the ways you can do this is by using elbow plots. Finally, I'll just mention that the reinforcement learning, the concept is you have an agent, maybe it's a car, self-driving car, you have a state and reward action, and so you go through and you create a feedback loop where you're actually able to reward a car enough so that it stays on the track. And that's really the kind of the basic intuition with self-driving cars. And you can see here, this is a function where we have some parameters that come in, and if the distance from maybe the center of the track is less than 1, we give it a reward. If it's greater, then we give it less of a reward. And so you can actually train the reinforcement learning algorithm based on a reward system. Here's another example. We maybe want to reward this for staying inside of a couple different parts of the track. But in general, those are the three main categories. Another thing to point out when you're doing machine learning is that most likely you want to start off with doing some foundational data science. I like to recommend you do ingestion phase, exploratory data analysis phase, modeling phase, and conclusion. So ingest would be, I would say, some of the data engineering aspects of your project. So can I get the data into the cloud, for example? EDA would be kind of explore it, visualize it, look at the patterns. Modeling would be, okay, can I come up with a prediction of some kind? And then a conclusion is, do we even do anything with this? I could come up with a model, for example, but if it's not actionable, then really there's no conclusion. We could just say the conclusion is we have no idea. And it's important to know about these four different phases. So here's an example of a project I did with COVID-19 data. And you can see I grabbed some data from the New York Times. I look at the exploratory data analysis, and at the time we could see the different states, visualize what's happening. And then later I could create a model that says, maybe how many people would get COVID, or, how to give people vaccines, or whatever it is I'm trying to solve. And then the conclusion would be then we give a report to somebody. And I think this is one of the biggest problems with data science industry is a lot of times people will create models, but there's no way to have an action for that model. And so does it even matter that you created a model if the business leaders or the leaders in government can't do anything with the model? So they must be actionable. So really that all leads us to this final step here, which is if we have all those things together, how would we build a machine learning pipeline from zero? And this is a good example. In this case, I'm using Microsoft Azure, but it could be AWS, it could be Google Cloud, it could be any other cloud. But the core concept of an ML pipeline is, again, I would start with data science, make sure you have that data science workflow. But then I would go through here and make sure that you're having your source code trigger the larger machine learning platform. In this case, there's something called Azure Pipelines that can deploy the model to their serverless environment, Azure App Services. That then runs a microservice called Flask, and then it serves out a machine learning API. So the steps to get this running, if you were going to go through and recreate this exact project, which you can, would be create a Python virtual environment, which we did, install the packages, run the code locally, and then test out the prediction. And I think, in fact, I've got this code. It's called Flask ML Server. Let's go ahead and take a look at this real quick. If I go to this and I go to Flask ML Azure Serverless, this looks like, so this is this project. It would be pretty straightforward actually to run this locally. I could just click on this code and copy it. Now with Cloud9 environment here, one of the things to be aware of is that you do have to set up SSH keys if you haven't set those up. So I would do this. I would say SSH keygen -t RSA, create these keys, and then you want to print this out like this, and then put these keys into GitHub. And that's how you initially, you only have to do this once, but that's how you get the ability to communicate with a repository. So I would go to settings, go to SSH and GPG keys, create a new one, call this MLOps, create this key. There we go. And now that I've got this, I should be able to go back to this, and I could say git clone, go to this Flask repo here, copy this, and then clone it like that. There we go. And then once I'm in here, because I've already set up a scaffolding here inside of my project with a makefile like that, in theory, I should be able to just say make install. Like this, make install, and we'll go through, install the packages, get it all working. So once you've set up proper scaffolding and automation, then it really does become much, much easier to deploy something into a production environment. And that's why the automation and the proper set of procedures is so important when you're building a machine learning pipeline, because it's completely reproducible, because you have really done the upfront work. I think that's one of the most important aspects of doing machine learning operations, is getting the proper structure, getting the scaffolding set up. And now if I want to say make test, right, I could run my test, or I want to say make lint. I could lint my code to make sure that it works properly. And I have some automation occurring where I know there's a level of quality with my project. So it's going through here. We see that everything looks like it works. So if I go back to this and I say, what did I want to run? I want to run Python app.py. Let's go ahead and do that. So we'll say Python app.py. Now it's running this prediction in foreground. And so we have a web server running. I could open up one more here, new terminal, and then I could do cd into this directory. And I have a bash script here called make predict. You can see this thing right there. There's my make predict. And I could actually go through here and I could say, make predict.sh. There we go. And we could go through and we could run our predictions. So in a nutshell, I think the main takeaway here is that it's important to have a foundational component where you're able to, create a scaffolding, install your packages, and then once you've done that and test it automatically, you can go through here and verify that your machine learning application works in production. So these are really the steps where I'm showing you would go through, set up the resources inside of the cloud environment, get your build server working, and then finally, when you get to the very bottom here, go through and deploy your code. So the nutshell here for MLOps is that, if we go back here, is all MLOps type solutions fit somewhere similar with this kind of a pattern, where you have your code, you check it out, you have a build server somewhere that verifies that your code works, you automatically deploy that to a cloud-based environment, and then you do a prediction based